Hey everyone, let's just take a collective deep breath and explore something kind of fascinating together. In this explainer, we're going to look at a natural phenomenon that we usually treat as this massive, frustrating engineering failure, but we're going to completely reframe it today. We're looking at corrosion, not as an enemy we have to defeat, but as a peaceful, totally inevitable return to balance. We'll calmly break down the exact factors that influence this process. It's actually really simple to understand, and honestly, it might just change the way you look at the engineered world around you.
So let's dive into a seemingly simple question that really shifts our perspective. Have you ever wondered why a shiny new car or a massive steel bridge just eventually surrenders to rust? It kind of feels like nature is constantly trying to undo all of our hard work, right? But what if nature isn't actually attacking our metals at all? What if, instead, the metals themselves are just tired? Let's look at the sheer scale of this before we get into the chemistry.
Just to ground this in reality, take a look at this number. A staggering 30 to 40% of the iron and steel we produce every single year is used just to replace materials that have rusted away. I mean, we're spending billions of dollars globally across cars, planes, basic infrastructure, simply replacing stuff that's already returned to the earth. The energy and cost are just monumental. It literally exceeds the damage from natural disasters like floods or hurricanes. So what exactly is driving this relentless cycle? Well, the absolutely crucial point here is that metals are thermodynamically unstable. Think about it. When we mine an ore, we use massive amounts of heat and energy to strip away oxygen and extract that pure metal. That extraction process is endothermic. It absorbs energy. So because these pure metals are packed with this artificial high energy, they're essentially sitting in an excited, highly stressed state. They just want to rest. Corrosion is literally just that endothermic extraction process running in reverse. The metal is calmly releasing that pent-up energy, interacting with its environment, and just going back to its stable resting state as a mineral. Now, what's really cool is how we can map out the entire recipe for rust into two totally calm, manageable categories. We don't need to get bogged down in crazy complex electrochemistry here. The rate at which a metal returns to its resting state really just depends on a delicate dance between two groups of factors. First, we have the primary factors, which are all about the metal's inner world, its own nature and geometry. And then we have the secondary factors, which represent the environment's mood, the external conditions surrounding that metal. So let's start with section 1, the metal's inner world, primary factors. Let's look inward first. We're going to examine how a metal's own composition dictates its journey back to the earth. It turns out how a metal is made holds the key to how quickly it decays. Let's compare pure and impure metals. When we look at pure metals, we see harmony. Because their structure is super homogeneous, they're highly resistant to corrosion, and they decay very, very slowly. But, as you know, most of our engineering metals aren't perfectly pure. They're mixed with other elements. When impurities, like lead or iron, are hanging out in a metal like zinc, the structure becomes heterogeneous. And this lack of harmony creates these tiny, stressful microelectrical cells right on the surface. The pure parts act as an anode, the impurities act as a cathode, and suddenly the metal just quietly starts consuming itself, speeding up its own decay. Basically, purity brings stability, while impurity brings inner conflict. And this brilliantly illustrates another inner factor, the position of metals in the Galvanic Series. When two different metals are in contact, they interact electrically. But how fast they decay depends on how mismatched they are. Think of it kind of like a difference in water pressure. The potential difference between iron and copper is pretty large, about 0.78 volts. That large galvanic gap creates a really strong electrochemical pull, causing the iron to corrode super fast. But iron and tin? They only have a 0.30 volt difference, so the pull is gentler and the decay is way slower. If you want a peaceful design, you've absolutely got to avoid placing highly mismatched metals right next to each other. Moving right along to section 2, the environment's influence, secondary factors. Let's look at how the world around the metal acts as a gentle or sometimes pretty aggressive catalyst. Look, even the most unstable metal won't corrode quickly if the environment doesn't provide the right conditions to carry the electrical charge. Just like a hot, incredibly humid summer day makes us feel completely drained, the environment has a massive effect on metals. High temperatures speed up the diffusion of ions and crank up the rate of chemical reactions. Humidity is totally essential too, because moisture in the air provides the liquid water needed to create an electrolyte, the medium that actually lets electrons flow. And finally, pH level is huge. A lower, highly acidic pH acts aggressively on the surface, rapidly stripping away electrons and spiking the rate of decay. On the flip side, alkaline environments can actually help certain metals form a nice, protective passive layer. Which brings us to Section 3, the size mismatch, anode to cathode ratio. Now we arrive at a fascinating geometric factor that heavily influences this natural return. It's this wild interplay between the physical design of a structure and the chemistry happening on its surface. We call it the size mismatch between anodic and cathodic areas. This fatal imbalance happens when the area giving up electrons, the anode, is tiny compared to the area receiving them, the cathode. Imagine a massive crowd of people all trying to squeeze through one single tiny doorway at the exact same time. The demand is huge, but the pathway is just too small. In corrosion, a giant cathode demands a massive flow of electrons to fuel its reactions, and it pulls all of those electrons from a very small anodic area. This forces a really intense, deeply destructive reaction into a super small, stressed space, leading to rapid, localized failure. Looking at this perfectly mundane wire fence, you can see this exact principle playing out right in front of us. Notice how the rusting isn't even at all. The pitting corrosion is happening exactly where the wires cross. And why is that? Well, because those areas trap tiny drops of moisture and they're less exposed to the oxygen in the air. So these tiny, less aerated spots become small anodes, while the rest of the highly oxygenated fence acts as one massive cathode. Those little joints are literally bearing the brunt of the decay, basically sacrificing themselves for the rest of the structure. This concept perfectly explains a classic engineering dilemma. Imagine you have a sheet of iron, and you want to protect it. If you coat it in tin, which is less active than iron, and you get even a tiny scratch, disaster strikes. That tiny scratch exposes the iron, turning it into a super small anode, while the massive surface of the tin acts as a cathode. The result? Rapid, intense rusting right at that tiny scratch. But if you coat that exact same iron in zinc, a process you probably know as galvanizing, and you scorch it, something beautiful happens. Zinc is more active than iron, so the mass of zinc coating becomes the anode, and the tiny scratch of exposed iron becomes the cathode. Because the anode is so large and relaxed, the corrosion of the zinc happens incredibly slowly, keeping the iron underneath totally safe. And finally, Section 4, a peaceful conclusion, finding balance. Let's wrap up our lo-fi study session today with a little shift in perspective. We've looked at the chemistry, the environment, and the geometry of corrosion. But how does this actually change the way we approach design? Consider this quote and really let it sink in. Corrosion is just an engineered material returning home to the earth. If we remember that this is literally just nature seeking its resting state, our job as engineers or scientists or even just curious observers isn't to fight this futile war against rust. I mean, we can never permanently stop thermodynamics, right? Instead, our role is to intelligently guide the environment and the materials to find a lasting, harmonious balance. We can use pure metals, we can match galvanic potentials carefully, and we can intentionally design large sacrificial anodes to gracefully accept that decay. So, the real takeaway here is this. The next time you look at a rusted bridge, a failing battery, or just an old wire fence, don't just see decay. See the energy returning to the earth, and ask yourself, how can we design our world to better flow with nature's tendency for balance? How can we create structures that accommodate this natural return, rather than fighting it until they inevitably fail? Thanks so much for joining me for this explainer. Keep asking those great questions, keep designing thoughtfully, and I'll see you all next time.